Hello and welcome to our lab on momentum and energy. The lab is in two parts. For our first part, we have a flat track. Now this track is level, and on it are two carts. And I can determine the mass of these carts using a pad balance. And in fact, for this particular experiment, I'm going to make this cart a little more massive. Now I have a motion sensor down here. It can see this cart with the cell on it. And so as I move this cart, it can tell me this velocity of the cart. However, it doesn't know the velocity of this cart. This cart is invisible to the motion sensor. However, when I run this experiment, I'm going to run this, I'm going to make a collision of this cart with the heavier cart. And when I do that, they stick together. But continue to move down the track at a slower velocity than the initial cart. So let's sort of take a look at what we might predict the motion sensor would see when that happens. So let's imagine that we're making a graph of velocity versus time. So here's our velocity versus time graph. And so as that cart was moving down the track, pretty constant velocity, suddenly there's a collision. And now the two carts are moving together. Of course, it's still just seeing the one cart at a lower constant velocity. And so this first velocity, right before the collision, I'm going to call that, let's call that V initial. And the velocity just after the collision, let's call that V final. You'll be able to do this by inspecting your velocity versus time graph generated by the motion sensor. Now, we're going to talk about momentum here. Momentum, a P here, for momentum obviously, is equal to mv, mass times velocity. So the initial momentum of this entire system, now remember the second cart was initially stationary, so the entire momentum of the system before the collision was just this first rolling cart. Its mass, m1, times v initial. Now after the collision, you have two carts rolling. You have m1 times v final, that's the final momentum of that cart. It has lost momentum. However, the stationary cart, the heavier one, m2, has gained momentum. So it's moving also with the speed of v final, and it has a mass, m2. So you have two carts with this speed, and so you have, that's your momentum. The total mass of the carts times the speed. So hopefully, if the conservation of momentum law holds true, then through this collision, very few non-conservative forces at work, a little bit of friction in there, not a lot, but hopefully, to within a small amount of error, your initial momentum is equal to the final momentum because momentum is conserved. And so that's what we call the conservation of momentum. Now there's another thing we can look at, and that is this idea of impulse. Impulse obviously is J, and so that's equal to a change in momentum, delta P. And impulse is also related to force times time. That's also equal to force times time. Now the next thing I want to talk about is impulse. Impulse obviously is J, and that's equal to a change in momentum. It's also equal to, as it turns out, force, so the average force, times time, a change in time. And so when we had that collision, each of those carts underwent a force during the collision. There was an average force on the carts in the opposite directions. The stationary cart had a force that way. The rolling cart that hit the stationary cart had a force back that way. And Newton's third law says that those forces are equal in magnitude. And so if those two forces are equal in magnitude, and of course they experience the same delta t, the same time of collision because they're colliding with each other, then what that tells me is the change in momentum of the first cart has to equal in magnitude the change in momentum of the second cart. Delta P is going to be the same for each. So that tells me that this cart, it's going from V initial times M1 is its momentum, and it's dropping down to V final times M1. It's experiencing a change in momentum, delta P, which is the impulse. And so, however, the stationary cart is undergoing a positive change in momentum. It's going from zero momentum, being stationary, to having a momentum of m2 v final. Its momentum increases. Now, if Newton's law holds true, then the change in momentum of the first cart is equal in magnitude to the change in momentum of the second cart, just in the opposite direction. So that's impulse. Now, the last thing I want to analyze with this particular collision is energy. I think I mentioned before that momentum is conserved in a collision. However, energy is not. And so if you look at the kinetic energy, a potential energy of these carts really doesn't change. It's on a level track. However, if we look at the kinetic energy, we notice that from one side of the collision to the other, there seems to be a change in total kinetic energy. Before the collision, the total kinetic energy is just the energy, kinetic energy of this first cart, which is 1/2 mv squared. This is m1 and v initial. After the collision, you've got the kinetic energy of those two carts that are stuck together. So you've got m2 plus m1 is the total mass, and then v final is the speed. So 1/2 total mass times v final squared. You find out that those two energies are not the same. There's been a decrease in the total kinetic energy, and therefore the total energy of this system. Energy has been lost to the surroundings.